So I want to talk today about doing continuous delivery in a machine learning context. Or when I say machine learning, what I really should be talking about is data-driven applications. So it could be machine learning. It could be something that we could call machine learning if we put a paint job on it. Or it could just be building things based on data overall. And really what this talk is about is much of what we heard this morning in Jez and Dave's opening keynote. It has a lot to do with the organizational realities and less to do with the actual technological realities of how we structure our teams, our organizations, and our systems. But I do think there is something different about data-driven systems that requires or merits special consideration when we talk about continuous delivery. And so what I want to talk about today is some of the patterns and pains that I have seen over the past few years as a consultant, working with clients and companies who are trying to build systems around their data. So by way of a brief introduction, my name is Emily Gorcenski. I work for ThoughtWorks in Germany. They were nice enough to let me come out here and talk with you all. For those who don't know, ThoughtWorks is a global consultancy, and we have done some famous things, I guess. But one of them is the technology radar. So we published this, we're on volume 21 now, and the reason I bring this up isn't just for marketing purposes, but to point out that what I'm talking about today, continuous delivery for machine learning, along with several other data-driven techniques, practices, et cetera, have been creeping up on our technology radar over the past couple of editions. And we actually have CD for ML in our trial stage, which is like the second highest stage on our technology radar. So we think it's important because we know that data is important. And if data is important, we want to help people build things with data the right way. So normally when we give this talk, we've given this talk about continuous delivery for machine learning a few different times, and we love to brag about oh, we're ThoughtWorks, we invented continuous delivery. And then we put up this quote, except both of these people are in the room right now. So it's a little bit awkward. But if you disagree with this, you don't have to come to me about it. You can talk to them. But continuous delivery is the ability to get changes of all types into the hands of users safely, quickly, and sustainably. So if that's our North Star for doing continuous delivery for machine learning, what does that mean in the data context? For me, as a data scientist, what that means is that continuous delivery makes my life easier. Regardless of all of the other benefits that hopefully we all know about by now, continuous delivery is a way of making my work get into production faster and easier. And as a data scientist, I struggle with that. And the reason that I struggle with that is because there are more impediments to shipping data products than there are to shipping software products. And the core truth of this is that it's important for us to do this because machine learning models have a shelf life. You can train a model, you can build a model, you can derive an insight, but the minute you derive that insight, it's already old news. And the longer you wait to get it into production, the less value you can get out of it. So my argument is that doing continuous delivery for data products is even more important than doing it for software products. But of course, it is harder. And so I want to talk a little bit about how it is harder than sort of conventional software, which I like to call deterministic systems. Even though maybe they're not quite deterministic, we want them to be, right? That's not necessarily true for machine learning. Machine learning, we know it's a non-deterministic process. In a deterministic system, we want it to be reproducible. We want it to be testable and auditable. We want to do things that continuously improve this. So every commit that we make should make the software better, and then we can test it. We can run all of these various million different types of tests, unit testing, integration testing, smoke testing, whatever. By contrast, data-driven systems usually have complex acceptance criteria. For example, let's say you're building a chatbot, and you want the chatbot to book your vacation. So you say, chatbot, I would like to fly to London. And the chatbot says, OK, when would you like to fly to London? And you might tell it. And then you might come back and say, chatbot, I would like to fly to Buenos Aires. And then it says, I'm sorry, your credit card is invalid. Is that an acceptance test or is that a unit test? We don't really know how to cut those boundaries. Data-driven systems are often black boxes. We don't know how to explain them. They just we crunch them on data and then magic happens, hopefully. And they're also highly nonlinear, which means that they're difficult to patch. A small change that can have a small effect locally can have a massive and unpredictable effect somewhere far away that we can't measure until something fails. So that's one way that data-driven systems are more difficult. The way that we structure product development in data-driven systems is also different. Here, in a deterministic system, we often take requirements from the user or from a consumer. Those requirements, therefore, flow downwards, and then we can build the system to meet them. Usually, there's some discoverable truth value. I would like the system to respond in under a minute. I would like, when this button clicks, this form appears. And we can generally observe the behavior of that system. We can hook up logging to it. We can do tracing. We can use all the lots of cool observability tools that we have, even for complex distributed systems. But in data-driven systems, the insights often flow upwards from the data. I can't say to you, I want you to build me a fraud detection algorithm that eliminates fraud if your data doesn't have that information that allows you to eliminate that fraud. So the insights have to flow upwards. There might be multiple values of a truth, or the truth might never be discoverable in a data-driven system. We can know this consumer bought this article of clothing on this date, but we can't ever know what led them to make that decision. What was the thing in their mind? We can write surveys, we can call them, we can look at NPS, whatever, but we don't actually know what the truth is. And then we also have this effect where we can observe the system and change its behavior. Not always, but we get some quantum physics stuff going on sometimes when we actually build data-driven systems. Finally, deterministic systems, we're very good at abstracting them. We have lots of best practices, right? You can look at the refactoring book. You can look at the patterns, software patterns book, the Gang of Four for lots of different ways to build software. We have functional paradigms that we can code without side effects, all sorts of stuff. We know how to do that. But in data-driven systems, the data can't be abstracted. It tells you what it tells you, nothing more and nothing less. A single counterexample disproves a hypothesis in mathematics. The same is true in data. You can build a system, but all you need is one piece of data that has unexpected behavior, and it can break everything. And then it's funny because I'm a mathematician by trade, or by training, and people often come to me and they say, oh, you must really love functional programming because you're a mathematician, right? It's just like doing math. And I say, well, I do love functional programming, but all that category theory stuff that you all talk about, us mathematicians call that generalized abstract nonsense. Because it's not actually useful when it comes to building theorems and proofs. And in a similar way, it's not always useful in building data-driven systems, which are concrete and messy. So data-driven development is hard, and the truth is that we're right now, currently, all kind of bad at it. But that's okay. There's nothing wrong with that. We want to get better. That's the whole point. So to talk about how to get better, I want to introduce a concept that I take from my background as a computational mathematician and an engineer working in complex engineering systems in aerospace and biotechnology. There's this concept called a technical readiness level. This was developed by NASA sometime in the 70s or 80s. And I love this model as long as you don't hold it too tightly. Because what it does is it gives us a way of measuring the state of readiness of complex engineered systems from research at the fundamental level to deployment. And the core bit of TRL is that as long as you don't take it too seriously, it gives you a really good way of measuring what type of work you should expect to be needing to do to get a system to the next level. Which is a way of saying that if you want to work on a data-driven system where you don't know what models are possible, it's a totally different way of working than if you have your requirements and you just need to ship software. And so when Jez and Dave were talking today about the sort of two different phases, you have your deployment phase of doing software where we can do things quickly and fast and we can estimate because everything is concrete, and then we have the design or the development phase. I like to call it the discovery phase, which is open-ended and we have no idea. Sometimes it could take us a minute to come up with the model. Sometimes it might seem obvious and then 7 months later we're still working on the basic thing. So rather than thinking in terms of how do we ship things using our standard ways of working, I like to think of where are we in our technical readiness, what types of thinking should I apply to the problem, and what are my expectations over what the output is. So in that sense, doing continuous delivery for machine learning is a process of transitioning the technology from research to productionized states. And at different stages, we need different skills. And one last note, as I go into the next phase of this talk, is that I don't want us to forget about BI systems when we talk about machine learning. Because the truth is there's not a whole lot of conceptual difference between machine learning and business intelligence. And I'll get into this a little bit later in a more abstract theoretical way. But there's also another point, and that is that data scientists often need support from data engineering teams in order to do their work, especially when it comes to productionizing data science products. But most of our data engineering workload, in some organizations at least, is taken up by supporting BI systems. And so we don't have a lot of free time to have those data engineers enabling data scientists to build data-driven products. So if we're talking about continuous delivery in an organizational transformation sense, we can't just say, oh, BI, they're just operations, product, whatever people, we don't care about them. We actually want to think about our entire data landscape and they're part of it. So when we give this talk, or when I give this talk about just how to do continuous delivery for machine learning, I like to say that there are 7 things that we need in our stack. The first is discoverable and accessible data. Obviously, we need to get to the data if we're going to build a data-driven product. But if we can't discover it, if we can't access it, or if it takes very long, then we're not working in a continuous delivery sort of way. So this is maybe the data governance problem that we all sort of understand. We also need version control and artifact repositories. Much like software development, we use Git or Bitbucket or whatever our favorite tool of choice is. But this becomes more complex when we talk about data and models, because models that are trained and compiled can be very large. They can be in the gigabytes, and our data can be in the terabytes sometimes. And so it becomes difficult to version control that. So how do you roll from one state to another when you have these massive artifacts floating around? And so we need some good way of maintaining a notion of version for our model, our data, and our software, and how those all tie together. We need a continuous delivery orchestration tool that is able to combine pipelines. The term pipeline has multiple meanings. Obviously, we can talk about CI/CD pipelines, we can talk about model training pipelines, we can talk about data pipelines. There's sort of a fractal or self-similar nature in all of this, and a good CI/CD tool will allow us to build sort of a parallelizable, scalable approach to all of these pipelines to get to that one single state for continuous delivery. Also important is the ability to run multiple environments and experiments in our infrastructure, ideally our production infrastructure. So this is a step beyond sort of test staging prod. We actually want to be able to run parallel experiments in production, which means that we have to have infrastructure that can support that. And this can be much more complicated than simply running feature flags. It can be much more complicated than running blue-green deploys or something like that. Finally, we need to, this is unique to machine learning, we need to have model performance assessment tracking. So we need to be able to evaluate the performance of our models in a targeted way. So this could be seen as experimental tracking, so what our data scientists are doing in their notebooks or in their labs. And it can also be seen as observability of the model in production. And naturally, we need monitoring and observability, not just for our infrastructure, but for the models themselves in our production environment. Now, I've actually run out of space in this slide, and we normally just do it with the 6, but there's a missing piece here, and that missing piece is testing. We need a comprehensive way of testing data, and that can be at ingestion time, at training time, at acceptance time. And we need a way of generating experiments that make sense. So if you have a non-deterministic piece of software, you need to be able to come up with test cases. And oftentimes, the test cases that we can come up with as humans are not sufficient to cover the span of what that machine learning model needs to or will operate on. So tools that can more accurately characterize the distribution of our inputs and our outputs to that model are necessary. So that said, I want to get into the fun part, also known as the part where Emily complains about things. So these are 5 things that I've seen that have really hurt businesses and teams. And so the first of them is perhaps a little bit weird coming from a data scientist, but there are too many data scientists often. Not generally, like I really want people to get into data science. Please, if you want to study data science, do it. But what I'm seeing often is because data science is a new field and there's still no we're only starting to get to formal training for data science as a profession. There's a few different paths to it, and one of them is academics. So lots of times we find academics shifting into industry, and they don't have software engineering experience. And enterprises will typically hire multiple PhD-level people to work in data science teams, and then they'll put them all together. And then what happens is you get like 4 to 8 data scientists working on a team with little to no software engineering support. And then what they do is they approach the problem like an academic would approach the problem. They run experiments, they set up controlled trials, they do prototype development, they kind of hack things together. But this doesn't move things towards production. And because many of these experiments take a long time, they tend to take on more work. And so a super common anti-pattern that I see is a team of data scientists with 3 or 4 or 5 different parallel work streams, each of them, or combined, all taking 12 to 24 months to get into production at the same time. That is not efficient. That doesn't work. Furthermore, I see all the time people looking for PhDs in data science. You probably don't need to hire a PhD to do data scientists or to do data science in your organization. Because the problems that you have probably don't require that hyper-specialized knowledge. But if you do need to hire a PhD, you damn well better make sure that you're surrounding them with people that have the similar degree of software delivery experience. So if you need that hotshot PhD out of Berkeley or whatever, make sure they have a data engineer, make sure they have a software engineer, make sure they have an infrastructure person, helping them get their work into production. Because academics don't have delivery pressure that looks like industry. They have other types of delivery pressure. And this is also something that needs to be said. And one of the things that we see is that academic coding practices struggle with quality. When we're talking about quality engineering and using continuous delivery to drive quality of software forward, we have to look critically at the way that we write some of this code. And this goes to tooling, which I'll talk about in a moment, but also the actual patterns. And so this is just from it doesn't matter what this is from. This code is fine for what it was written for, which is academic R&D. But you can't productionize this. This is 30 lines of a 300-line method with no documentation, no tests, and inline lambdas defined that do one thing. This snippet of code is doing like 30 things in 30 lines, and we want to have, and this is part of just one function, right? So we want one function to do one thing. We can't write code like this in a production environment. But when we hire PhDs to do data science, we give them a senior title, and then nobody is willing to tell them, you can't write code like this anymore. The second thing that we have is overcomplicated solutioning. Because one thing that is true is that everyone thinks that their competitors have a super AI. everywhere. And you can talk to two people who are direct competitors with each other, and they are both convinced that the other one has this brilliant AI that they are using to leverage massive competitive advantage. And so what happens is people are jumping to the most complicated things right away, often because they're hiring PhDs from academia who specialize in neural networks or whatever, and they don't want to implement a logistic regression, which anyone can do if they know how. It's not even that hard, which is a pattern of looking for problems where solutions exist to the cool stuff, right? So all of the big wins in deep learning and all that stuff, they exist in a narrow subset of problems that we have. So like computer vision, if you don't have a computer vision problem, don't look for a computer vision solution. So this is one thing that happens. So most of the time, we often say like 90% of your use cases, you just need logistic regression. And the other thing is, if you can't ship a logistic regression, even if it's not perfect, you definitely can't ship a convolutional neural network. And on top of that, the more complex your method, the more diminishing returns you have. Which means if you have a deterministic system and you want to go data-driven, you're going to get your biggest benefit from going from nothing to a logistic regression solution that is OK. And then going from that to the next more complicated thing is only going to get you a more marginal increase. And your increases are going to get more and more marginal the more complex they get. But that is very valid for many use cases. So if that's what you need to do, you need to build up to that. So we need to, again, develop iteratively. The next pattern is that the wrong tools are being used. We like to work in notebooks as data scientists. Notebooks are great for prototyping and experimentation, which is good. We want our data scientists to do science. We want them to experiment. But we can't productionize that. And at some point, we have to shift the code out of the notebook and into something that looks like production quality software. That's a hard thing to do. And if you don't have people who know how to write production quality software, that transition often happens too late. So there's another side of this, and that is that because of this pattern of using notebooks, we often skimp on things like version control practices, because you have a notebook server, right? All your code's up there. But then you start decoupling your work from your production builds, and then we try to solve that problem with more tooling. The second problem with tooling is that the existing tools are attempting to do way too much. They're cutting across the wrong planes. They're doing things like data versioning plus Kubernetes deployments. You're like, what? Those two things don't belong together. So that's another thing that we are seeing. I need to speed it up a little bit. The fourth problem that I often come across is that the wrong metrics are being used to evaluate our systems. Machine learning accuracy, whatever it is, your AOC values, that's all cool, but prove it to me that that links to money. And tell me how. Because it doesn't matter if you're building a better classifier if that marginal gain doesn't actually equate to something that has business value. The flip side of this coin, that's sort of like the product level, the operational level, is that the SRE community has done a good job at evangelizing things like SLAs and SLOs, but we're often writing them around things like distributed systems performance, which doesn't make sense in a data context per se. So instead of doing things like building SLAs around data availability, data freshness, data accuracy, we're doing things like, what is the response time of my BI system? We don't care about what that is. What we care about is that BI system up to date and accurate at 8 in the morning when our BI analysts need that data? Finally, talking about BI, there's too many dashboards. This affects startups more than enterprises, though it does affect enterprises. I've been at places where I've seen more than one dashboard per person in the company. A piece of data should give you an insight and if it gives you that insight, you have to have a path to action. If I'm in Oracle, not the Oracle database, but like the one that sits in the mountain in Greece, and I tell you something about your business, can you act on it right away? Probably, in some cases, yes, and in some cases, no. But the problem is that when we start building many, many dashboards, they start containing many, many pieces of information. And if one of those pieces of information starts telling us something interesting and unexpected, we're often not in a position to be able to do something about it. And this explosion of dashboards has other problems. They're built on code that is not version controlled, it's not testable, it's highly interdependent, and it creates a massive amount of technical debt. But yet, we're building critical business operations, financial decisions, legal decisions, product decisions, plan for next year around this way too often, and we don't have a sense of the quality of what those truths are telling us. So we probably can't act on more than 4 or 5 things at once, which means that your team probably needs one dashboard with 4 or 5 things on it, and that's it. So those are the things I'm complaining about. So what works? So I'm going to quickly go through some theoretical stuff and talk about control theory. So a closed-loop controller looks like this. You have a controller, a plant, which is a process or a model, and sensors. And so this is the fundamental closed-loop controller that affects every dynamical system, from an airplane or an automobile to a business that runs and changes over time. What this can be broken down to is the things that you can control. That's our controller. And then you have external inputs, which might be information about the user or the environment or the business or the economy. The plant is how your system will behave. What will your users do in response to an input? The output of that plant is what is. That's the truth. But then you have what you can measure, your sensors. And that's what you can observe. That's your data. So when we talk about data, what we're talking about is a filtered estimate of reality. Data is a snapshot of the universe at a point in time. And so there's a few things that we can do when we're building data-driven products. We can build better experiences, better models, etc. And then we can also improve our data capture process. We can measure things more quickly, more accurately, more often. We can make it easier. This is what we actually do when we're doing data engineering and data development. Moreover, when we talk about machine learning, and this is why I wanted to bring BI into this talk, is that machine learning, we often talk about as one thing, but it can live in 2 different places. It can either be a way of understanding our process by developing a better model, understanding how our customers buy things, or it can be taking and changing their experience to try to induce them to buy something else. So it could be, give me the demographics of who's buying what products. That's kind of a BI thing. Or it could be, build me a recommendation engine, right? So machine learning can live in both places. A data-driven system has to integrate all of this. So there's different components, and so we need to understand what stage we are at this. So what works? Enablement over self-service. Self-service BI is great, but if we want to build a data-driven product, let's focus on building things vertically, not horizontal platforms, but vertical products. We know that standalone teams of data scientists don't work, but also integrating data scientists into cross-functional teams doesn't work. As soon as you start a data-driven product, have a delivery plan for day 1. Give people a second for photos. I have 2 more slides and I'm done. Test many things at once. So running shadow models in production is a great way to assess model performance, which is why we need complex infrastructure. There's nothing that says you can only run 1 production model. You just only want to take the output of 1 production model. You can run 2, 3, 20 in prod at the same time. And if you're even smart, you can switch between them at will. So your versioning is not monotonic anymore. That's why it's complex. But one caveat for this is that open loop performance is not the same as closed loop performance. Finally, build a wormhole between your teams. One of the things that we see, the DevOps revolution was about bringing development and operations organizationally together, which means we want to take our product decisions and our data people and our data sources and put them closer together. So we don't want many horizontal platform teams in between. We want to get them working together. So one thing that I'm trying to promote is try a 3-team maximum from source to product. So maybe a team that produces or maintains the data, one that builds the product, and then you can have a team in between to enable that communication, that technology transition. And then finally, the more teams you have between your data capture and your next iteration, the more delays you implement. So every team induces a delay. And if you have many, many, many teams, you're going to have many, many, many delays, which means that by the time you actually produce that insight, it's already expired. That's all I've got. Thank you very much. We'll have a discussion next. And some of my ThoughtWorks colleagues have written some really amazing things. If the slides are available later, you can click on all those things. But I'll put those up there if you want some photos.
And Emily, thank you very much.
Thank you.
So challenges, since you were discussing about the Jupyter notebooks and how common they are, at our company, we have a situation where the data scientists are using Jupyter notebooks, and then those notebooks are basically given to an engineering team to productize and rewritten in a different language at the same time, which to me, I don't know if this is a good pattern or if there's a better solution, there must be, but how people deal with that.
A bit of a challenge, ideas?
Sure. It can be a good pattern. It could also be an anti-pattern. It really depends on your organization and how closely those teams and those people are working together. If you have the money and the time to invest in that, that's fine. That's certainly how many big organizations do it. They just let their data scientists do data science things and not worry about the production. But that doesn't work for every organization. Not every organization can afford an entire team of data engineers or software engineers to support an entire team of data scientists. And I think that that's the more common situation. And so I think that there's sort of a diversity of sub-roles within data science. Some data scientists need to be more focused on how do I build the production artifact, and some need to be more focused on how do I explore the data to get to what I need to get to build a product and to make it go forward. So.
I'm wondering, have you seen specific problems from that at your organization?
I'm relatively new to the organization, so I was kind of shocked when I heard that these data models, which are the basis of our entire business, were being transcribed from one language to another by a completely different team. It seems to be working, but
it feels weird. It seems, yeah, worrying. Okay. Sorry, put your hand up.
Oh, I have a new topic. Is that okay? So I know almost nothing about this area, but the product that our company has includes dashboards with insights, which some of which are generated by machine learning models. When you say too many dashboards and they should be actionable things, are you talking about for the development team, or are you talking about for the customers in a product?
Generally, it can depend. If it's a customer for a product and they want many dashboards, that's what you give them. But for a team, generally speaking, I think that if you size a team around 6 or 8 people, you can usually get away with 1 or 2 dashboards effectively. And that might require some careful thinking about what is and isn't necessary, and what are you using that information for.
Any other challenges?
Yep. I was wondering, you mentioned that large data sets are a problem for versioning. Do you have patterns that you've seen work really well? Or is that hey, it would be really nice if somebody solved this?
So just to avoid it turning into a Q&A for Emily, if there's other folks who I'm going to give priority to other folks who might have a response to that. It's fine if Emily to have a response as well, but just going to answer.
I can tell you what. Okay. Sure. So there's a tool that I like to use called DVC. It's a nice little lightweight Git wrapper for versioning data, and it can work with all sorts of cloud storage services. DVC is great for model development because it doesn't try to do too much. And then there's some really interesting stuff being developed around Delta Lakes, which kind of have the versioning of large data baked in. And I'm working with some Delta Lake stuff right now, and it's freaking awesome.
say one challenge I'm kind of curious about if anybody has solved this. So I'm working with a lot of my customers. I work at Puppet, so we do operations kind of side of things. And a lot of my customers are asking me, we have this data science team, we have our application teams. How do we set up a self-service infrastructure for a lot of these teams to be able to be autonomous, but still be able to hand off things in between them so that you can keep up with the business, but still not like break things all the time? And I can say things like, yeah, you need TensorFlow serving, you need weights and biases, you need all of these tooling. But then they say, great, how do we pull it all together? How does Puppet provision the infrastructure? How do these services hand off between them? And that's where I have absolutely no answer for them, and I'm wondering if anybody does.
I might have a partial response to that. A data science team that I worked closely with spent a lot of time with the product team early in, sort of coming to an agreement about what the shape of a model would look like, and ultimately built an API between the model team and the whole rest of the product. And that led to this very nice world where, like, they had the dummy model, which they could run through continuous integration and testing and all that sort of thing, and the UI could change all around it. And meanwhile, the modeling people were working over here on their stuff, and once in a while they'd come in with, here's the newer model, and they knew that it would slot in because it had to fit against the API and it had to fit against the test cases. And then they'd also be able to come in with the improved tests of, like, we always know it should return a hotel, we always know it should return 23, we always know it should not understand the following query. But that's very much an open loop system, not a closed loop system.
Oh, I was going to add one thing. If you have that contract and you have a new version of the model, an extra benefit that you get is you can actually compare the old and the new and be sure that you're actually improving the state of the world as opposed to just pushing new bits.
How? Like, what do you actually use to do that? Sorry, I'm breaking the rules. How do you actually do that? Like, what tools do people use?
There's a couple tools. I would say that A/B testing and dark launches can be really useful. So you can actually say, hey, for 5% of our requests, we're going to send it to both models. Okay. And we're going to compare their results. And, hey, we're just going to record where they were different. And then we can go back, look at it later and be like, was this answer better or was it worse?
That makes sense.
All right, are we ready to move on to the next one? Successes. It's kind of a newer area. Success. Yes, yes. A lot of smiling and nodding, but no one's saying anything.
So I'm actually going to ask if people have had successes in this area. So it doesn't like say a success, but I'm curious, based on the descriptions there, right? We talked about how isolating data scientists didn't seem to be very successful. Embedding them with product teams didn't seem very successful. I'm curious what models people had success then with working with data scientists that we saw, like what are some operating models that we were able to be successful? I think you highlighted maybe something there. And the other question maybe that kind of goes with that is, I'm also curious, one of the things I think we benefit from in the industry a lot of times is seeing people that have types of delivery that might be in some ways similar to us. And I don't know that I've seen out there a lot of great examples of what effective machine learning pipelines might look like as they interact with maybe software or in different domains. And I'm curious if people have had some successes or examples that I'm just not seeing out there. I know, that was kind of lame, not a success. But.
I was ready to do this thing. Hi, I work at Textio. We are very, very machine learning heavy, and natural language processing in particular. The thing that we do is that feature-driven product work is centered around data science and NLP, and then there are tiers of support teams that support that, but it's not a trade-off, it's a supporting action. So as you get farther away, the frequency of the support goes down, but it tends to become larger. So like I sit on an infrastructure team about once a month, like data science would be like, I need a whole new AWS account. And I'm like, Christ. But that's the singular blocking action. And it's happened at least like, it was like Q4, Q3 or something. We were having a lot of product launches. I happened to catch all of the infantry on-call requests, and they each took me a total of 2 weeks, a few days each. And then at the end of it, I was like, wow, so much happened. I don't even know what it was. And then like one of the C-levels was like, that was like our biggest product launch of the quarter. And I was like, oh, right. I had no idea, but data science did. Right, and they have a similar setup with the Python services teams where data scientists keep going, and then, I'm going to pull you into my repo to write one Lambda, right, to hook into my notebook, and then I'm going to keep going, right? What that produces is it really emphasizes the learning and the like get out of the way on the point of view of like the services and the infrastructure people. And we spend a lot of time like giving like very, very tactical learning sessions to data scientists, things like how to debug AWS something, 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 or how to do feature flags. Oh my gosh, there's so much about like feature flags and CI and like Git, stuff like that.
Thank you. One success. So one success that I did see with a customer is actually similar to the embedding with the ops team, is they built a tool that would use a TensorFlow serving and provide an API to the data science team to be able to ship out a model and turn it on or off for different parts of the infrastructure. And the app team wrote just a simple little Docker image that could be spun up and connect out to TensorFlow serving to grab the appropriate model for that time. So that way the data science team didn't actually need to write much code at all. They weren't writing any code that went into production. They were just controlling the model. And of course, that did require a lot of collaboration with the app team if they ever needed to add parameters to the, the classification call or anything like that. That was a conversation that needed to be had. But it meant that everybody was able to be autonomy on both sides of that wall.
I had one follow-up there that you sort of made me think of. Going back to the versioning thing, keeping your old models so that you can run input on them and say, hey, what was the answer going to be, several months ago? I've seen that be really useful a couple of times.
One of the interesting things about data is that the meaning and the value of data changes over time, even if the data itself doesn't. And I think that too often, like when in software, we always just kind of move forward, and the old versions are just the past. But data that is a week old means one thing, and data that is a month old means a different thing, and data from last year is a different thing entirely. And so the ability to continue to extract value from that data, I think, is important, but it's not always the same value. So what you were saying about being able to run multiple models, old models, compare them, I think is still super relevant.
So I think it's time to move to the one that's probably going to be the most fun, the wish list. Does anybody have anything they'd like to see in 2 to 5 years? Oh, come on.
All right, sure, I'll go. I want to see the enterprise tooling. I want to see the one tool that glues together all of the other tools, so you have one business input to see exactly the entire pipeline from concept to production and that closed loop system. That does not exist today. All of our customers are having to glue all of it together themselves and learn all this bespoke tooling and become, have developed their own PhDs in infrastructure delivery, and it's absolutely bonkers, and enterprises can't do it.
One thing that strikes me about that is, so one of the things that Emily mentioned was around the tooling and the fact that some of the tools are trying to do too many different things that don't fit together, which kind of sounds like, well, we need different tools, each that does one thing well, which is kind of in some ways the opposite of like having one, it does mean that you end up gluing a whole bunch of stuff together. So I don't know how we reconcile those two tensions, I guess.
Honestly, I look at it a lot like what CD tools became now. Like you have GitLab, for example, or now GitHub Actions. They don't do everything. They call out to other things, but they are able to provide that glue layer. And I want to see that for CD for ML.
Yeah, that's exactly it. I want to see a CI/CD tool built with machine learning and data as a first-class citizen. I want the user face. I want the options. I want all of that to be able to specify everything I want to do around data, much in the same way that we can do things like specify around testing. We can specify around integration testing versus unit testing in many of our CD environments now. Better build parallelism, better ability to toggle builds conditionally based on whatever. Even with tools like Circle right now, it's really hard to integrate, to do a training and an integration in one step.
So that's essentially arguing for like if I understand right, it's the config as code except all the way through the modeling as code and, wow, sorry, brain melting a little.
One of the things pragmatically, it feels to me like it's a step in the direction there is systems like KF serving that build your model into a Docker container, which give you some of the versioning and so forth. The problem is today, when you end up with a 3 gig Docker container or a 20 gig Docker container, the infrastructure gets a little sad about that. And I'm looking forward to better tools for materializing those on hosts more efficiently.
I think I'd actually rather see like a Docker type tool that is smart to machine learning rather than a machine learning tool that can then build Docker around it, right? So, like I don't take a Rails framework or a Java framework and then say, okay, like now I need to like put a plugin in this that makes it Docker, or like I put it into a Docker image, right? And I would like to see more tooling like that, where we can just focus on the machine learning development, and then we can put it in, like the tool like itself is like, oh, okay, this is what I'm expecting.
The tool knows how to produce the Docker, right? Rather than making the data scientists need to learn Docker.
So we have a couple more minutes. There must be some other wish list items.
I have one more thing. I want to see a testing framework that works in notebooks, because we're not going to get data scientists away from notebooks. So like, give me a good integrated testing framework that I can one button click and test my notebook.
One more time, thank you for joining us, and thank you for participating.